Okay. Here we are. We are on the last inferential test for proportion, or last inferential process for proportion. So far, what we've done is we've done one sample intervals, one sample test, two sample intervals, and now we're doing two sample tests. So let's go ahead and just take a look and see what kind of process we have that we talked about today. So today, what we dealt with was which grade is more likely to go to prom. Student council at a large high school is wondering if juniors or seniors are more likely to attend prom. They take a random sample of 50 juniors and find that 28 are planning to attend prom. They take a random sample of 45 seniors and 29 are planning to attend prom. Okay, so now we're going to use phantoms here, kind of like we did with one sample test, but with a two sample test, what we're going to do is we have to do it. We have to do the checks on both. And there's one new thing here, and it's the only time in any of these inferential processes that something different happens. So when we go to P, it's still going to be declaring our parameters in context. So again, in this case, what I would say is the first thing I would say is I'd say that PS is the true proportion of seniors who would attend prom. And then we would look at PJ, would be the true proportion of juniors who would attend prom. And what we're really concerned with more than anything else, was we're actually concerned with is PS minus PJ, because it says, do the data provide convincing evidence that a higher proportion of seniors are going? So in this case, we're going to look at PS minus PJ, and this is called the true difference of proportions, plural. So now, first thing again, just a reminder, we are never, ever going to put a number up here. There's never any numbers. There's never any sample up here. It's all parameters. So this is what we are looking for. This is the real answer. We don't know the real answer, so up here there'll never be any sort of numbers. Okay. Next thing is we have hypotheses, and as always, there's going to be a null and there's going to be an alternative. And I'm going to tell you that in this two sample world, much like in the interval where we were looking for 0, PS minus PJ equals 0, that there is no difference. The null hypothesis is that they're the same. You may also see it written like this, PS equals PJ. That's just another way of saying the same thing. It's basically saying that they're the same. Either one is fine. Whichever one makes more sense to you is the one I want you to go with. The alternative, we want to see that seniors are higher. So what that means is PS minus PJ would be greater than 0, or PS is greater than PJ. So again, let me talk about the hypotheses thing. The null hypothesis will always be an equal sign. And I will tell you in the two sample world, it will almost always be equal to 0. The only time it won't be equal to 0 is if the problem clearly states it. The alternative will be one of three symbols. It'll be a greater than, it'll be a less than, or it'll be a not equal to. It'll never be a greater than or equal to, it'll never be a less than or equal to. So I have my hypotheses, my null and my alternative. Now what I need to do is I need to validate my assumptions. So here's everything is pretty much what we've always done. So the first one is random. So we're going to say both stated as random. Okay. Next thing we're going to check is we're going to check independent. Okay, so we're going to check independent. And the independent check is going to be that 10n check. So what I'm going to do down here is I'm going to say 10 times my number of seniors. So 10 times 45 is 450. I want to compare that to my population of seniors. I'm going to do 10 times my number of juniors. So 10 times 50. That's 500. I'm going to compare that to my number of juniors. And what I'm going to say is, if I'm not sure, I'm going to say I'm going to assume, but I'm going to say safe to assume more than 450 seniors and 500 juniors at a large high school. And the other thing we always want to do is we always need to address the independence with the two samples of each other. And I can say that juniors and seniors are independent of each other. So you want to make sure you say both of those. So there's my independence check. Okay. So far, everything is pretty much the same. Here's where my first change comes, and the biggest change. And it's the only time that this happens. Because the large enough check, I am going to create a new proportion. So what I do know is I do know the fact of this. I know the fact that in this case right here, that P hat seniors is going to be 29 out of 45, which is 0.64. I know that P hat juniors is 28 out of 50. I know that that's going to be 0.56, so 0.644. Now here's the deal. This is a little different because the null hypothesis is I'm assuming that the two groups are the same. What happens in just the two sample test, this doesn't happen in the interval, just the test, is I create this thing and it's called the pooled sample. Basically what I mean by pooled is this: if juniors and seniors are in sense the same, if there's no difference between the two, then I could just roll them all together into one giant sample. So what happens is, because of my null hypothesis, I create this new pooled proportion, and it's called P hat C is usually how it's referred to. And what it's going to be is it's going to be my number of senior successes, my number of junior successes, over my number of seniors plus my number of juniors. So in this case, it's going to be 28 plus 29 over 45 plus 50. And if I do that, it's going to be 60%. That's called pooled. So if I put everybody in the same gigantic group, so all 95 of them, 60% of them would be going to prom. So that's because of that null hypothesis that I do it, because the large enough check is actually based on that. What I'm going to do is I'm going to say, well, if I have that number of seniors and I multiply it times that P hat C. So if I take my 45 seniors and I multiply it times 60%, I get 27. That's greater than or equal to 10. If I take my number of seniors and I multiply it times the complement, 45 times 0.4 is going to give me 18. So if in fact there was no difference, I would be assured of having enough senior successes and enough senior failures. And then I'm going to do the same thing for juniors. Yeah, C equals 50 times 0.6, that's 30. That's greater than or equal to 10. And junior failures, 1 minus P hat C, 50 times 0.4 gives me 20. That's greater than or equal to 10. So I have the large enough count, but I base it on the pooled data. And we're going to use that pooled data again as well. But that's what we need to do. We need to do pooled. Okay. So that's a difference. We need to talk. We need to be aware of that. That's something new. And now, N part, we are going to conduct a 2-sample z-test for true PS minus PJ at, and in this case, it says 5% significance at alpha equals 0.05. So that's what we're going to do. We're going to conduct a, and again, if you think about it, this is that like kind of sentence. We're going to do 2-sample z-test, true difference of proportions at that significance level. And now let me show you the formula. I'm going to write the formula down first, and then I'm going to write it down with the numbers plugged in. This is what the formula is. It would be P hat seniors minus P hat juniors minus P senior probability junior. So we're trying to figure out the difference in the samples versus the difference in the parameters. And the difference that's going to come here is I'm going to use the pooled proportion down here over the sample size of seniors plus the pooled proportion number of juniors. So I'm going to base the standard deviation on the pooled proportion. And just so you know, when I go to do this on my formula sheet, I look right here. It talks about this one here, but when P1 equals P2 is assumed, I'm going to use this one down here. Now, this looks weird, but it's just because they factored the P hat C out, but they give you that pooled one, and that's just for 2 samples. So in this case, what I want to do is I want to write this down, and I'm going to put down values. So now, P hat S is 0.644. P hat J is 0.56. Now, here's the thing, PS minus PJ, we have said it's 0. I'm going to tell you it's almost always going to be that 0 there. And what now I'm going to do is I'm going to fill in the blanks down here. I got my P hat C of 0.6, 1 minus 0.6 over my sample size for seniors is 45, plus 0.6, 1 minus 0.6 over my sample size of 50. So what this is, again, I'm basing this on that there's no difference. Because there's no difference, I use this pooled proportion down there. It's the only time we're going to do that, only time. And now what I'm going to do is I'm going to pick up my calculator, and my calculator is going to simplify that for me. What I'm going to do is I am going to go to stat. I'm going to go to tests, and I'm going to do number 6. With Mr. Mike in the Skittles, you did number 5, so I'm going to do number 6. And what I'm going to do here is I'm going to go ahead and put in my proportion. So let's start with seniors. It was 29 seniors out of 45. It was 28 seniors out of 50. And what I want to do is I want to look at that null hypothesis is greater than. So I want to make sure I pick the greater than sign and pick it. And now I'm going to go ahead and do calculate. And when I do calculate, I'm going to get a z-score of 0.839. So we're going to get a z-score here of 0.839. I'm going to get a z-score of 0.839. And I am going to get a p-value of, sorry, right here, right this, 0.2008. So again, my p-value here is 0.2008. So on this one, my p-value is going to be 0.2008. Over here. So again, I'm reading this right out here, 0.8388 or 0.8389 is my z-score. This is my p-value. This is the seniors proportion. This is the juniors proportion. This is the pooled proportion. So lots of p's. So now what I have is I have my z-score. I'm barely a standard deviation above average. My p-value is 0.2008. And I'm going to make my conclusion. So what I do is I compare my p-value. And my p-value of 0.2008, I'm going to compare it to my alpha of 0.05. It is greater than. We are going to fail to reject. We're going to fail to reject the null. And then we're going to use this sentence. And again, it's safe to use this sentence since the p-value of 0.2008 is greater than alpha of 0.05. We fail to reject the null hypothesis. There is not evidence to support the claim that a higher proportion of seniors are going to the prom than juniors. Okay, so again, this final sentence, and let me just kind of emphasize this again. When College Board goes to assess this, these are the things that they're looking for. They are looking for a comparison of the p-value to the alpha. They're looking for that. That's one thing that they're looking for. The next thing that they're looking for is based on that, they're looking for what conclusion would you draw? The next thing that they're going to look for based on that is they're going to look for what that means in context of the alternative. So there's not evidence. And then as always, we always want to have context. So this is, again, what College Board looks for when they do something like this. They are looking for all of this information. This is why that I typically am giving you these boilerplates to do, because I want you to kind of ensure you get the points. Now, when all is said and done, I will be honest with you. These two steps right here, this O and the M, are not critical as long as you address it down here in the S. The reason I break out O and M is because a lot of times people forget to explicitly list the p-value, and people forget to, this reminds you to make your decision. So it kind of forces you to do it. But if you were to just go from this step right here and to this S, that would be fine because you're addressing everything. You said the p-value, you showed your decision. But this is what a two-sample test looks like. And again, the big difference is this idea right here. This pooling is something that we need to keep track of. And that is for two-sample proportion tests. That's it. Nowhere else are we going to do this. So the easiest way I want to show you is, notice when we did this in the calculator, when we did calc and we did our test, notice we went through and entered all this data. What I'm going to do is give you a sneak preview of what we're going to do when we go to means. When we do means, we're going to do stat test. And what we're going to do is a two-sample t-test. A two-sample t-test is, I went the wrong way. So here's a two-sample t-test. This is what we're going to be doing next unit. And what I want you to notice is notice it says pool down here. Easiest way to remember this is if your calculator asks you to pool something, you say no, because the calculator by default pools the data for proportions. So hopefully that helps. We're now done with all of our proportion inferential processes. We're going to learn about the types of errors that we can make in the next class. So when I see you all again on Monday, we're going to go over the types of errors we can make. And then Wednesday of next week, we're going to do our review, but that's going to set us up for our test. And our test is going to, again, be on just proportions. So there'll be a free response question. And again, I can tell you, easiest thing in the world to understand on this. You are going to have 2 free response questions. You are going to have a 1-sample question. You're going to have a 2-sample question. You're going to have a proportion question. You're going to have a test question. So if you think about that, that's 4 ideas, mix and match them. You're going to have a 1-sample test in a 2-sample interval, or you're going to have a 2-sample test and a 1-sample interval together. So that's going to be what we're going to be working towards. Once we get done with this unit, we're going to dive into means. And means is going to go a little bit quicker than this because honestly, the whole process is the same. What's going to happen is when we go to do some of this process, like one of the checks here changes and the formula obviously changes, but in general, the process is the same. So please let me know if you have any questions. We are almost done with that first inferential process, and then we'll be moving on to the next one.